Hey everyone, I want to pick up where we left off. We were discussing cosets, and I should say cosets, when it comes to group theory, the study of group theory, and additionally when we study, next quarter, right, in the study of rings, the idea of coset is one of the key concepts. So this is not something to blow off. This is something that you definitely want to understand. So we last time showed that the set of cosets, left cosets, and then there's also right cosets, but the set of left cosets forms a partition of a group G. And so there's some notation that goes along here. So let's say if H is a subgroup of G, then we write it like this: G slash H. This right here stands for the set of left cosets. So this is equal to the set of all left cosets, so G times H, where G runs through all of G. You read this G modulo H. All right, so this is said G modulo H. Typically, I shorten that. Most people will just say G mod H is how you'd actually say that. So G mod H. In the study of groups, the left cosets are the ones that come up the most. Right, so G mod H. When we say it, we usually are referring to this, but there's also the set of right cosets, and even the notation is a little bit clunky. Right, it's written like that. So H with a slash, you want to indicate that the H is sort of you can think of it as kind of a denominator of sorts. And so this is the set of all right cosets. So H, G, or little g, runs through all of capital G. All right, so we're going to be very interested in the set of cosets, especially the set of left cosets. And another piece of terminology here. So any element of GH is a left coset representative. So, okay, now let's look at some examples. So if I do Z mod 4Z, right, so 4Z is a subgroup. Now, who this ends up being is 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, and 3 plus 4Z. I think last time we did the example where I was looking at 6Z and there ended up being 6 cosets. And then it starts repeating itself. Same thing here, except we have 4 cosets and then they start repeating themselves. Another example, Sn mod An. So remember, Sn, that's the symmetric group, and then An is the alternating group, and the An occupies exactly half of Sn, right, the set of even cosets. And so Sn mod An consists of Sn itself, that's the identity times Sn, and then one other coset, say 1, 2 times Sn. Right, so this makes up the entire set of left cosets, Sn mod An. And I should point out, I wrote here 0 plus 4n. This is typically just abbreviated. I just said 4n. 0 plus 4z is typically abbreviated. When you have the identity here, you often just don't write it. You just think of the subgroup H in general as one of the cosets. Okay, so now we're ready for a theorem. So this is theorem 10.2, and it's called Lagrange's theorem. And so it goes like this. Let's let G be a finite group. And then we're going to need a subgroup. So now we'll say it like this. So if H is a subgroup of G, then the order of H divides the order the order of G. So divides, there's a cleaner way to write it. So if we have a finite group and any subgroup, then the order of the subgroup divides the order of the group. And so for the proof, this is a nice theorem, and the proof is sort of correspondingly slick. So here's how it goes. So let's pick any element. So let's pick little g in capital G, and we're going to define a function, and it's going to go, so it's going to be phi from H to the coset G times H, and we'll do it in the obvious way. And I should point out, this is a function, not a homomorphism, because GH, unless G is the identity, G times H is not even a subgroup. So we're going to define this mapping right here in the obvious way, so it's going to be defined by phi of little h equals little g times little h. It's easy to show. I'll just say check. I mean, it's almost obvious, so we'll just say, I'll say check rather than clearly. So check that phi is a bijection. I mean, it's practically obvious, but it's worthwhile for you to go through and just verify it for yourselves. So what does that tell us then? It tells us that these two sets have the same size, right? The same cardinality. So it follows that the order of H is equal to the cardinality of the coset G times H. So how do we interpret that? Well, we chose this little g at random and showed that the left coset has to have the same size, right, the same cardinality as H does. And because G was chosen arbitrarily, what that tells us is that all left cosets have the same size, right? They have the same size. So as a consequence, all left cosets have the same cardinality. Now, we start off with a finite group. So since G is finite, there exists some left coset representatives. So G1 up through, let's say, Gn in capital G, such that if you want to list all the cosets, this collection right here is sufficient when it comes to representatives. So such that G mod H is equal to G1 H up through Gn H. Right, so that gives us a complete listing of the left cosets. Now, what do we know? We know that G is going to be the union of these cosets because the set of left cosets forms a partition. So now we have G equals the union. I equals 1 to n Gi times H. And what do we know? We know that all of the cosets are disjoint. So we can say, and so, if we want to count the size of G, we could do so by counting up the sizes, the cardinalities of each of these cosets. So the order of G is equal to cardinality of G1H plus ... plus cardinality of Gn times H. but all of those have the same size, so this is equal to n, because there are n of them, times the order of h. That's exactly what we needed, right? We wanted to show that the order of h divides the order of g, which means that g is a multiple of the order of h. All right, that completes the proof, so we can say, therefore, the order of h divides the order of g. All right, so that's a pretty slick proof, right? Show that the cosets all have the same size by displaying, not displaying, what word am I looking for? Well, concocting a bijection between cosets, right? So we know they all have the same size. List out G mod H. We know previously that we've got a partition, and so this union is disjoint, which means that when we want to count the size of G, we count, right, the orders or the cardinalities of each of these sets here individually and add them together, right? Because they all have the same size, we can write it as n times the order of H. That's what we needed. And so here's a nice quick consequence. Actually, we've got a couple of consequences. So here's one. So corollary 10.3, if the order of G is prime, then G is cyclic. That's actually kind of an amazing, I mean, just looking at that statement, that's crazy, right? Take any group, no matter how big, as long as it's a finite group. If it has prime order, then it has to be a cyclic group. That's a pretty strong statement. And so it goes like this. There's something to prove here. So let's write order of G equal to P, where P is prime. Now, I want to choose any non-trivial element in G. So let's let, it doesn't matter who it is, let little g be an element of G minus, right, I just want to subtract off the identity. So we chose a non-trivial element of G. Now what that means is, since it's not equal to the identity, there has to be more than one element in the cyclic subgroup generated by G. So then, all right, the cyclic subgroup generated by G has order greater than or equal to 2. Now, by Lagrange's theorem, the order of G has to divide P. So by Lagrange, the order of G, order of the cyclic subgroup generated by G divides P, and since this is not 2, it's got to be equal to P. Since this is not 1, it's got to be equal to P. So, therefore, the order of the subgroup generated by G is equal to P. And what does that mean then? It means that this cyclic subgroup right here fills out all of G. In other words, little g is a generator for capital G. So that's pretty cool. Another one. So, and this one's sort of obvious. There's nothing to prove here. So corollary 10.4. I've kind of alluded to this previously in the cyclic. Well, we know this in the cyclic case, and now we know it more generally. So if G is finite and little g is an element of capital G, then the order of little g divides the order of the group capital G. That's automatic because by definition the order of little g is the order of the cyclic subgroup generated by little g. I'm just checking the time there. Yeah, okay. I got a little bit more to say here. Yeah, okay, so this sort of leads to a definition now that we've got Lagrange's theorem in place. So let's let H be a subgroup of G. The index of H in G is, and well, let's write it like this. It's the cardinality, so this is the cardinality of G mod H. So in the finite case, it's the number of cosets. More generally, it's the cardinality of the set of cosets. And it's denoted square bracket G colon H. Oh, denoted. So for example, the index of 4z in z is equal to 4 because there are 4 left cosets as we saw in a previous example. The index of an in s of n is equal to 2 because there are exactly 2 cosets corresponding to an. One thing to be aware of, so let's say note, when G is finite, the index can be computed fairly easily, right? It's just the order of G divided by the order of H, right? That's straight from Lagrange. One thing that's true, so here's an example. The index of the set of integers in the rational numbers, right? So the index of z in Q is infinity. And I want to say, oh no, I thought I was going to give it as a homework, but I'll just explain why. So the reason. So what do I need to do? I need to show you that there's an infinite number of left cosets, and so the cosets. Here's the reason. So the cosets of the form 1 over n plus z, where are, well, so these are distinct for all little n in z, right? So for all integers. So that provides an infinite number of cosets. That's not necessarily all of the cosets, but this guarantees that we have an infinite number of cosets. The index behaves nicely with respect to sort of nested collections of subgroups. And so let's say this as a theorem. So this is going to be theorem 10.5. So let's take some subgroups now. So let's let, I'm going to call them K, H, and G. So let's let K be a subgroup of H, which is a subgroup of G. Now, if the index of G in H and the index of K, oh, I just said that backwards. If the index of H in G and the index of K in H are finite, then we have this nice formula that tells us that the index of k in G is multiplicative. It's equal to the index of G in H times, I said that backwards again, index of H in G times the index of K in H. So here's how the proof goes, right? What is this saying? It's saying that the number of left cosets of K can be computed by multiplying the number of left cosets of H in G times the number of left cosets of K in H. So, so it's basically just a counting argument. So let's let G1 up through G sub, what do I use here, an M, be a set of left coset representatives for no, I'm going to do K, right? Oh no, I'm doing H. So this is for G mod H. Which means then that G mod H is equal to G1 times H up through GM times H. And then similarly, so I need, I want left cosets for this part here too, so say, and similarly, we're going to have H mod K is going to have some H mod K. H mod K, we need left coset represents for that, and I'm going to use little h1 through little hn. So this will be h1 times k up through hn times k. So now, yeah, okay, so since, if we look at GI, GI times H intersect GJ times H is non-empty when I not equal to J. So we have a pairwise disjoint collection right here. It follows that, okay, so how do I want to write this? GI times H sub P K. H sub P times capital K intersect GJ H sub Q K. Is empty. Whenever, okay, and let me finish the sentence here. Whenever, so it's going to be I comma P is not equal to J comma Q. So that's kind of a mouthful here. So what's going on? Okay, we know that we have a partition, right? So we get disjointness here. And so now H is made up of these cosets right here. So if I take a coset, this is sitting inside H, this is sitting inside H. And so if I choose different cosets here, because of this equality or this disjointness, it gives us disjointness here. Okay, so what does that mean? Thus, so this collection is going to look a little bit weird here, but my cosets are going to be GI, so the set GI H, what did I use? GIHJ, H sub j times k, where I runs from 1 to m, and j runs from 1 to n, is, so this is a pairwise disjoint set of left cosets. Now, what do I know? Well, since, let's do it over here. Since, if we look at one of the cosets, GI times H, right, that's going to equal, well, it'll equal GI times H1K union GI times H2K, and you go on all the way forever running through these cosets here. So union GI times H sub n. Okay. It follows that G is equal to well, I'm going to have to use a double union now. So union I equals 1 to m, union j equals 1 to n. GIHJ times capital K. And that's a capital K there. So what do we have then? We have a collection of left cosets that makes up all of G. How many of them are there? There's m times n of them, right? So G mod K is equal to the set of left cosets GIHJ times K, where 1 or I runs between 1 and m, and J runs from 1 to n. Right? How many of them are there? So this right here, there are m times n of them. So this is a collection of mn cosets, and that's exactly what we needed, right? We're trying to equate the number of cosets. Oh, sorry, that should not say G mod H. That's a G mod K there. All right, so we were trying to equate the number of cosets there with the product of the number of cosets of G mod H and H mod K. Right, so that does it. And actually, okay, that's a good place to stop right there. So we will see you next time.